Welcome back to the deep dive.
Great to be here.
Today we're tackling something, well, absolutely fundamental. Electricity. It powers everything, but it can feel a bit mysterious, right?
Oh, definitely. Especially concepts like voltage.
Exactly. So our mission today is to really demystify voltage, make it super intuitive, especially if you're just starting out with this stuff.
Yeah, break it down.
And we've got, I think, a pretty neat everyday analogy lined up that should make understanding how electricity flows, well, hopefully a breeze.
Looking forward to it.
Okay, let's unpack this. So, first things first. What is that invisible force? The thing that makes electricity actually flow through wires and power up our gadgets.
Right, that essential push, that driving force, that's what we call voltage.
Voltage.
It's the power behind, every electron moving in a circuit.
And you definitely see the numbers around, like 220 V marked on appliances here.
Yep, standard household voltage in many places.
Or you look at a little AA battery, and it says 1.5 V.
Much smaller, yeah.
And that V that stands for volts, right? Named after someone.
That's right. It's the unit named after the Italian physicist Alessandro Volta. He did pioneering work with batteries.
Ah, okay. Makes sense.
And what's really useful about the volt is that it gives us a standard way to measure this electrical push.
Measuring height in meters or feet?
Exactly. It lets us compare the electrical force everywhere, from a tiny chip inside your phone to, the huge power lines outside.
So it seems simple enough then. A bigger number before the V, bigger voltage, stronger push.
Pretty much. That 220V from your wall socket, it's pushing roughly 146 times harder than that 1.5V battery.
Wow. Okay. That's quite a difference.
It really is. And this leads directly to a really crucial point about safety.
Right. I was thinking about that. Higher voltage sounds riskier.
It is. Higher voltage means there's a potential for more current to flow. And if that current flows through us, through the human body, well, that's extremely dangerous.
So it's not just the voltage number itself.
No, it's about how that voltage interacts with resistance, like our body's resistance to create a current. That current is what causes harm. That's why even voltages that seem low can be dangerous in certain situations.
That's, a really important thing to remember. Safety first.
Always.
Yeah.
Engineers spend a lot of time designing things to be safe around these voltages.
It's just wild how much variety there is, though. Different voltages for different jobs.
Absolutely. Like people having different weights.
Yeah.
Voltages come in all sizes, tailored for the task.
Our sources listed quite a range, didn't they?
Oh, yeah. Fantastic spectrum. You start small, like a button battery, maybe 1.5V.
Tiny.
Your phone battery.
Yeah.
Maybe around 5V. Laptop, bit more, like 10.8V typically.
Okay.
Car battery, standard 12V. Then you jump up. Household power, we said 220V.
Right.
Big industrial motors might use 380V, but then you get into some really interesting stuff.
Right.
Like an electric eel, it can generate about 800V all by itself.
Seriously, for hunting.
Exactly. To stun prey. Nature's taser, basically.
That's incredible. What else? Higher.
Oh, much higher. Static electricity, that little shock you get from a doorknob. That could be 10,000V.
No way! 10,000! Feels like nothing compared to the eel.
Well, the current is incredibly tiny, thankfully. Then you've got the power grid. Local distribution lines might be around 22,900V.
Okay, getting serious now.
Those huge transmission towers carrying power across the country. 345,000 VV is common.
Wow.
And the ultimate. Lightning. We're talking about 1 billion volts, roughly.
1 billion? That's just hard to even comprehend.
It really is.
Okay, so we have all these numbers, these examples, from 1.5V to 1 billion volts. But I admit, voltage still feels a bit abstract. You can't see it.
That's a very common feeling. It's not tangible.
Which brings us to the analogy you mentioned. This is where hopefully it gets really interesting and starts to click.
Right. The best way, I think, the most intuitive way to grasp electricity and voltage specifically is to think of it like water.
Water. Okay, I use water every day. Tell me more.
Think about your tap. You turn it on, water comes out. Washing, laundry, dishes. You need that water to flow, right?
Yeah, and you want it to come out with some force, especially if you're rinsing something sticky. A weak trickle is useless.
Exactly. That force pushing the water through the pipes, that's hydraulic pressure.
Hydraulic pressure. Okay.
It's the pressure from the weight of the water pushing down. Strong pressure makes water shoot out far and high. Think of a powerful fountain.
Right. Needs loads of pressure.
And if the pressure is weak, you just get that sad little dribble. That's why we need pumps to get water up tall buildings.
Okay, so pressure is key for water flow. How do we get that strong pressure?
Well, you can use pumps, like you said, artificially create it, or naturally you can store a lot of water up high. Think of a dam.
Ah, like in hydroelectric power.
Precisely.
Yeah.
They build dams to hold water way up high. That height creates immense pressure at the bottom, which they use to spin turbines and generate electricity. The height creates the force.
So height matters.
It does. And another way to think about that pressure is water level. It's really about the difference in height, the difference in potential energy between 2 points.
Yeah.
Higher water level difference, stronger pressure.
Okay, water level difference, potential energy. I think I see where this is going. Bring it back to electricity for us.
Okay, that water level representing the water's potential force based on its position or height, that's the perfect analogy for electric potential.
Electric potential. So it's like the electrical height.
Kind of, yeah. It's the electrical potential energy per unit charge at a certain point in a circuit. But like water level, it's usually talked about as a difference between 2 points. It's relative.
A difference.
Yes, and here's the punchline. That difference in electric potential energy between 2 points, that is what we call voltage.
Ah, so voltage is the difference in electric potential, the electrical pressure difference.
Exactly. It's the electrical push caused by that difference in electrical height.
That clicks much better than just thinking about volts as numbers. It's a difference, a potential.
Right. And this helps clear up a common misunderstanding. Think about taking your temperature.
Okay, put a thermometer under my tongue or on my forehead. One spot.
Right. But you can never measure voltage at just one single point. It doesn't work that way.
Why not?
Because voltage is the difference between 2 points. Always. It's like using a tape measure, you need a start point and an end point to measure a length.
You can't measure length from just one end. Got it.
So voltage is always measured across something, or between 2 points.
That makes sense why multimeters, those electrical testers, always have 2 probes, 2 pointy bits.
Exactly. You need to touch those 2 probes to 2 different points in the circuit.
Like the 2 holes in a wall socket.
Perfect example. You put 1 probe in each hole, and the meter shows you the voltage difference between them, 220V or whatever it is where you live.
Or across the terminals of a battery.
Yep, plus to minus. If your meter reads 0V, it means there's no potential difference between those 2 points. No electrical pressure, so no current will flow between them. Could be a broken wire, dead battery, switch off.
Okay, always 2 points. But is there ever a situation where it feels like we measure at just 1 point? Sometimes you hear about voltage relative to ground.
Good question. Yes, there is, and it involves another analogy. Think about measuring the height of a mountain.
We say it's, 8,000 meters above sea level.
Exactly. Sea level is our agreed upon 0.0 meters, our reference for height.
Okay.
In electricity, we do something very similar. We use the Earth itself as a common reference point and define its electric potential as 0 volts.
The whole planet is 0V.
We define it that way for practical purposes. It's huge, it can absorb or supply a lot of charge without its potential changing much. So we connect circuits to the Earth. That's called grounding or earthing.
I've heard of grounding for safety, right?
Primarily, yes. It connects the circuit or equipment casing to that 0V potential of the Earth. This helps protect against shocks if something goes wrong, like a wire touching the metal case. It gives stray electricity a safe path to the ground.
So when people talk about voltage to ground,
they're measuring the voltage difference between a specific point in the circuit and that 0V reference, the Earth. So it looks like a single point measurement, but it's implicitly measuring the difference relative to ground. Zero.
Okay, that makes sense. It's always a difference, even if 1 point is the assumed 0 of the Earth.
Precisely.
Let's try and pull this all together then. For you listening, what's the big takeaway here?
I think the core idea is the water analogy. Water flows downhill from high water level to low water level because of the pressure difference, the hydraulic pressure.
Right.
Electricity, which is the flow of charge we call current, does the same thing. It flows from a point of high electric potential, high electrical height, to a point of low electric potential, low electrical height.
And the force pushing it, the pressure difference causing that flow, is the voltage.
That's it in a nutshell. Voltage drives the current.
So thinking about this connection, this fundamental principle, it really underpins almost everything electric, doesn't it?
It really does. Every time you plug something in, turn on a switch, use a battery,
Yeah.
you're essentially creating or utilizing a voltage difference, a potential difference, to make current flow and do useful work. Light a bulb, run a motor, power a computer.
It's the invisible engine behind it all.
You could say that.
So here's something to think about next time you interact with electricity. When you plug in your phone charger, or maybe you feel that zap of static electricity, or even if you see a huge flash of lightning.
1 billion volts.
Right. How might understanding voltage now, as this electrical pressure difference, this potential to push current, change how you see those everyday, or maybe not so everyday, electrical events?
It adds a layer of understanding to the hidden forces constantly at work around us. It's all about that push.